In this video, we will examine how interactive narrations can be used to promote learning in the classroom. Stories are deeply embedded in all of our cultures. The ability to use narrations likely predates the evolution of Homo sapiens. Narratives captivate humans. They help us to relate to each other and to make connections to the past and the possible future. Narratives also help us to preserve our cultural heritage. However, it is important that in the classroom, narratives not be used to passively entertain students. In the classroom, narratives should engage learners. An engaged learner is not simply enjoying the narrative. An engaged learner is focused on the presented information and is provoked into analyzing the information using their critical thinking skills. In order to do this, narratives in the classroom should not be passive storytelling sessions, but interactive sessions where the story is interwoven with Socratic questioning. In interactive storytelling, the teacher is not just a narrator. The teacher uses Socratic questioning to guide students' thinking and keep student discussion focused. The students push the story forward by recalling information required for the story to move and help to expand the story by explaining why and how things happen. They also make predictions and ask questions to shape how the story unfolds. At the end of the slide deck, a video of a sample lesson will play. It is a recording of me using an interactive narration to help students prepare for their biochemistry test. The lesson is not a perfect example of the process. Due to COVID, this lesson was delivered in a virtual setting, and I am still learning how to effectively deliver virtual lessons. Also, it should be noted that my students for this class did not like to talk in our virtual classes. They did engage, but only through texting. I am still trying to figure out how to get students comfortable with talking in virtual class. When you watch the video, please try to consider how the model blends the strengths of storytelling with the goals of Socratic questioning.
If you remember from the very, very beginning, we have first lab, we established that for a living cell you did your yeast lab, and you established that it appears that for a cell to live and grow and show all the signs of life, it needed a minimum of 2 requirements. What were the 2 fundamental things it needed to do that? Water, and not necessarily sugar. We use sugar, but what did we say the sugar likely was about? Energy. It's an energy source. So we need an energy source, which in the case of yeast, we thought that's what the sugar was playing the role for, and we needed the water. And what did we say was the role of water? Why do we need water to live? What is it about water that makes it a requirement? It's a solvent. That's right. That is the solvent. It allows our world as a cell to be a liquid world. It is a universal solvent. Most things, not all things, will dissolve in water, allowing the world to exist in a liquid state. And why do we care that our world is a liquid state? What's the advantage of a liquid state? Why not a solid state world for cells? Why not a gaseous state? What are we after? Why do you need a solvent? Because if not, then I would say you don't need water. You could have a solid base system and have that for a living system. We need things to collide with. Yes, it's about collisions, the collisions theory. So remember, the collision theory states that in order to have a chemical reaction, you are going to require collisions to occur with a high energy, with a sufficient amount of energy and the correct orientation. And since life is going to require a complex number of chemical reactions, ultimately it is a complex chemical system. It's not just a chemical system. We're going to see emergent properties with it, but at the heart of it is chemistry. And you need to have a world in which chemical reactions can be extremely high in their rate. And the first step in that is to have a lot of collisions. So you want a liquid state that keeps things moving, mobile, relatively close to each other, hopefully, and that they can collide. In addition, we're going to have to do things that will encourage a higher level of chemical reactions. It's not just as simple as throw things in water and it works. We need organization, we're going to need enzymes, etc. So all of those things are going to come up. But for today, what we're going to start with our focus is water. With water, you can have the possibility of life at least. And without water, you are not going to have a system that lives. Life cannot exist without a solvent. And in our case, it's going to be water. And we talked about the properties of water and why it's unlikely that any other liquid could take the place of water. That we were fairly confident that if life exists anywhere else in the universe, it is still going to be water-based because the properties of water allows it to be that universal solvent. Okay? So where this leads us to in real life is controlling. The first thing we're going to do is about controlling our ability to distribute food. Well, humans require an awful lot of food. We require it every day as long as we live. We don't store food for long periods of time. We're not like a whale that can fail to eat for 6 months and somehow be alive with it. We cannot store that energy in us. We have to intake the food approximately once a day. We could go a few days without it, but we are generally going to need our food on a daily basis. So that's the first thing. The second thing is we don't have food available being produced every day. Just because you need it doesn't mean you get it. If we live in a cold place, yes, that was my husband, sorry. This is not a professionally produced video. If you're in a real world scenario, if you're in a cold country, you are not going to get food every day. Wintertime is a hard time. So you have to be able to store food. If you can't store it in you, you have to be able to store it outside of you and have it available when you're ready. The other problem came as humans grew to larger communities, we become dependent on larger complex needs. To stay in a place and to live as a community means you're not hunting. That's not the only thing you do. You don't spend every day hunting. Hence, agriculture has to develop, and you have to be able to store your food. And some of the people in your community are not going to be involved with food production in the end. They're going to be dealing with things like building buildings and roads and government, which, doesn't even produce a product, right? So human civilization leads to an increasing need for food storage issues because fewer people produce the food and it has to be stored when it is produced. And so we have a variety of methods as humans that we've developed, and over time, we get more sophisticated with it. Probably the first one is just darn luck, because the rule is going to be, if it has water in it, living things can live in it, and therefore they can eat it and rot it. We don't want other things eating our food. We want to eat it. If it lacks water, then we can talk about how we could keep it. So some things it's easy, okay? Some things, once you harvest it, you just lie it out in the air for a bit and it would be dry and you can then store it. So we are very dependent. Our base of our diet comes from products that primarily are dryable, easy to dry, stored food products, grains. So this is rice. Pretty much you pick it, you beat the shell off of it. This is, modern day polished, but pretty much you pick it, you beat off the shell, you dry it, let it air dry a bit, put it in a box, and you're done, okay? And this can store. Today we can process it so well, it could probably store for a few years, but generally speaking, it could definitely store for a few months before there's still moisture in there. There's still things that will eat it, right? So it's not perfect, but that's how we start. There are many things then that start to be. So pretty much human preservation of food starts off with things that just are fairly dry to begin with, and that all it takes is a little sit out in the sun, right? And spices are easy to do like that. Cinnamon bark, it's the bark of the tree. It's pretty dry to begin with, then you just dry it out some more, and this can stay. This one's so dry, this could stay for probably longer than a human lifetime. This would stay. This probably will never go well. I'm sure given enough time, something might be obliterated, but not very much could live off of that. Okay, so that's a safe product. So as human civilizations expand, we have the ability not just to produce our food and store it for ourselves, but in areas where you could produce more, you could ship it around. You could move it around, but you're limited at first to the dry things. So the spice trade and the grains can move. And anything that's dry could move. But that is clearly, well, spice is nice and I love it in my food. It's not exactly a caloric thing. Rice, yes, but not so much the spice. Okay? Spices can help preserve other things, and so that's a good thing. But we have to start getting more sophisticated. So what's one of the oldest methods that you know of beyond simply just air drying things? How are we going to dry it if it's not up to the air? Salt, yes, salting things has been one of the oldest ways that we have. So we can salt even meat, which is so full of water, can be dried. This is a packet of saltfish. It's already been taken off, it's been mushed up and everything. It's all ready to go to make ackee and saltfish, so it's good to go. It's already processed and good to go for making my ackee and saltfish, but it's just dried meat. It is kept refrigerated still because that would improve it, but technically you could keep, if this is well-dried fish, you can keep this on the shelf, nothing required. In fact, when you go into like West Indian stores, etc., they don't put it in the fridge. You just get it on the shelf. And many of higher end, like more like the larger grocery stores, etc., they do put it in the fridge, and it's, of course, it's recommended. It's a meat product. Any additional methods to preserve it to make sure you don't have any spoilage is good. So having it in the fridge is a benefit, but not actually essential to keep this. Okay, I'm gonna put this back in my fridge. Freezer, actually. So salt becomes it. Now you explain to me, because you tell me, why is it that putting salt all over anything is going to be a benefit? How does that help the situation? How does that cause the drying? Tell me about it. You can use your microphone if you want, or you can type. How does it take moisture out of the food? It can't be magic. You need to explain this. So yes, it's a good start, but that won't score you points in a grade 12 bio. Come on, give me some words. Give me some explanation. What are we talking about here? Throw in some technical terms for me if you can. So I take a piece of food and I throw salt all over it. Now what? What will happen? Osmosis, good. All right, work this out for me. Tell me, why does it cause moisture to leave, and how is this about osmosis? So I take something, I take my fish, I lay it down, I lay salt all over it. What am I doing? I've created a hypertonic extracellular environment. Perfect. Yes, Marianne. I've created, sorry, I just with his name. I've created a hypertonic extracellular fluid. And now, thank you. And now moisture is going to flow via osmosis out of the cells into. Now, what will happen to my fish? How will it look? People do know you're smart. What will happen to the fish? What will the fish look like? Will it look like the same fish? The fish cells will shrivel. Yeah, it's going to get dehydrated and hard. And that is not the best for texture. It will change the texture, but we've become so used to it and we learn how to improve it. So when I take that salt fish out, I am not going to gnaw down on it. Like, seriously, that is not going to taste very good. And it won't be great for me. But what I will do is I can, so the other reason that piece is in the fridge. I have actually steamed, like I've actually put it in boiling water and I've boiled it at first to get out some of the salt because it's way too salty. So I've boiled it, so I've added moisture back in. That's why it has to be in the freezer now. So that's the other reason my fish is in the freezer. I've added back water and I've removed some of the salt, get it down, and so it's not a salt bucket for me. And then it's caused it to rehydrate a bit, so the texture is better. So now it's good to go for cooking. I just need to add it to the rest of the ingredients to make my dish. So the texture is going to change. There is no avoiding that. And most of our techniques, if they're going to depend upon osmosis, will fundamentally change the texture. Okay. Now, why do you think we use salt? Because there are other things we could have used to make a hypertonic extracellular solution. Why salt? Give me some of the reasons. There's more than one reason why salt is ideal. Could you give me some reason? It's cheap. Absolutely. Where do we get salt from? Where's our number one source for salt? Yes, the grocery store, but I'm kind of more talking about where humans get it from originally. The sea, yes. Now you can mine salt. There is salt deposits in the ground, which is not a surprise because the planet has been evolving over time. So places on ground may have been places in the ocean at one point in time. So we have salt deposits on land that we can mine, but that's actually a more expensive way and dangerous way to get salt. Probably the first way we humans were getting salt was straight out of salt water from the ocean. You just scoop up the salt water, you lay it out on some rocks and some shallow rocks that have a bit of a divot if you've made it or it naturally has it. Let the water evaporate off and voila, you've got salt. So it's extremely cheap. And you can ship it anywhere you want because if anything were to get into it, osmosis would kill it and it'll be safe. So this is transportable and cheap and easy. And so for the longest while, our preservation techniques were then down to two. First one, air drying things that were close to dry already. Option number two now is speed up the drying process so they can't rot while you're trying to dry it by using salt and driving the osmosis. That means you're going to get salty food though, and salt is not the only thing that we like. What else do we like? We like sweet. We love sweet. The problem with sweet though is sweet's actually a good thing. Think about it. Sweet is primarily caused by what kind of molecule? What molecule are we talking about when we talk sweet? Sugar, glucose, yeah, and table sugar. So we're talking usually about sucrose, but glucose, sucrose, fructose are our major sugars that we humans get naturally. And they're great for it because they don't go through the cell membrane. Tell me why. So salt doesn't go through the cell membrane and it's cheap. Tell me why salt didn't go through again. And so why it caused it, because in order to cause the osmosis, you want something that won't go through the cell membrane. Why didn't salt go through? It's ionic, that's right. It's an ionic compound. It can't go through the hydrophobic core of the cell membrane. Perfect. Okay, sugar is not ionic though. How come it can't go through the cell membrane? It's too big. That is fundamentally the reason. It is polar. It's a bit on the polar side, but it's not all the way to ionic. So it should go through, even if it's not the most efficient thing, except that it's so big, it's not going to go through. So it is also good for creating an osmotic concentration. And instead of salty food, you could get sweet food then. But there was a problem for the longest while. While sweet is something that people would love to preserve, it was very limited. Because when you think about it, where would you have gotten sugar from? What are the natural sources of sugar? I mean, salt is easy to get from the ocean, but where would you get sugar? Plants. Well, okay, but which plants? I mean, think about it. I eat plants all the time. Their sugar content's not that big, actually. Sugar cane. Aha. We're going to leave sugar cane out of this story for a bit, just for a bit. Honey. Yeah. Probably the only natural source of an extremely concentrated amount of sugar is honey. This is a slightly darker honey because it's blueberry. It's made from blueberry plants, so it's a little bit darker. It has a slight blueberry taste to it. Apparently, my daughter prefers the regular clover one. I won't buy this again. So I was buying it from the farmer's market, so I bought the blueberry one, but she didn't like that. Okay, so but it is still honey, even though it's dark. Okay, that is honey. And yeah, this is an important source of sugar and probably the only really sweet thing for humans for the longest while. Every other method of getting sugar from plants will require us to process it. So the indigenous native cultures from North America had a sugar source, which wasn't honey because they didn't have honeybees here. What were they using? They did have to process it to get it, but what did they use? What did native North Americans use as their sugar source? No. What's this? Maple syrup. But that's not really a natural product in the sense that I don't just take it out of the maple tree. To get this, yeah, this is a luxury product in this house. This is like my husband gets one bottle of this because this is genuine, pure, dark maple syrup. He gets one bottle of this for Christmas. It comes in his stocking. That's his supply for the year. And the reason that is so expensive, yes, thank you. The reason that is so expensive is that to make that little bottle, there would have been gallons of syrup taken out of the tree. The tree was tapped for, and it doesn't kill the tree. We take the sap out, that's right, he's right. It's called sap. We get the sap out of the tree, which comes out in springtime as the tree is returning nutrients up to the leaves so it can grow. We tap out a percentage of it. It does not damage the tree. I'm sure it slows the tree doesn't grow as fast, but it's a tree, it can handle that, okay? So we tap out some of the sap and we have to boil it down. So gallons and gallons of tree sap has been boiled to the point that you get a syrup. But the amount of boiling means that that is a precious, highly regulated source of sugar to the communities that learn to do that. It is a luxury product that is heavily traded and guarded and not used. You will not be using that to preserve food because that took too much energy. It is a premium thing. But somebody else said sugarcane. And when you think about it, sugarcane is the same thing. To get sugarcane, now sugarcane is a grass, and grass does grow faster than trees, so we can get more of it, that's true. But we are still going to be stuck with the same problem. We are going to have vast amounts of the sugar juice, sugarcane sap, squeezed out of that grass, and it's just a grass, granted a giant grass, squeeze it out and boil it down and take out, and not just some, because we're going to go for pure crystallized sugar. We are going to boil off every last drop of water till all we have is the pure solid sugar crystals left behind. Does that sound, if you think maple syrup was not going to be easy to have large quantities of, do you think it sounds plausible that sugarcane sugar, should be easily accessible to us? No. And yet, an entire world changes when this becomes available. So the first question is, how did we do it? How did we get so much glorious sugar for so cheap? You want a hint? Where's sugar produced? It's produced in many places now. It's mass produced, but where was the major production? Nowadays, there are several countries that make it, but it was produced where? There must be some of you whose family can answer that question. I know where it's made. Your families must know where it was made. The Caribbean. This comes from the Caribbean. How did we get so much? How could you produce so much and have all the energy? Too many old people selling it back home? Come on. Think about when sugar comes into our production like this, that you have so much, you can trade it around and send it around the world and everything else. What allowed this? This is the fruits of slavery. This is what we got from slavery. This is how it starts. When you think of slavery, you need to understand, what were we doing as humans? We had suddenly found a way to mass produce what we need and what we want. Those two things. Some of the things we need and some of the things we want. Vast quantities of food start to arrive and shipped around, but it's done through slavery. Mass numbers of people are abducted from one continent, shipped to another part of the world, and all they do for their entire life is to produce the plant that the sap will be taken out of. It will be boiled down and we will have sugar. And a narrative begins in our world that changes us fundamentally. For starters, some countries get very rich and an entire historical fallout comes from it. And I'm going to leave that for your history classes to go into. But in science, there's a fundamental shift in the chemistry of the kitchen, which we will get into. Because mass production of sugar changes the game for us. We don't get just sugar from this, which is a new product that is in such cheap, bountiful supply to create the osmosis in my kitchen. I get new things. I get rum, basis of most of our alcohols. Rum is a cheap and very easy to produce alcohol, which is sterilizing and which I can now also use to preserve things with. I get liquid forms of sugar that I can use because crystals aren't good for everything, but there are other things, and I get molasses. And it's so cheap that it's going to spread right throughout the world and fundamentally shift the cuisines of the world right across the world. So the slave trade starts off a massive change in cuisines across the world. And fundamental to that shift is sugar. And so today we're going to focus on causing osmosis through sugar. So much so, by the way, that you will see the cuisine and it will be like, yeah, but to get that cuisine, you could not have done it. So we think of places in the world that produce things for us. What's in this gold foil thing? Left over from Christmas too. Last one left. Everything's rationed in this house right now with the pandemic. What's in here? Chocolate. And you think of chocolate and you think of what places in the world? Where do you think of when you think of chocolate? Where does chocolate come from? Africa, yes. Africa, the Willy Wonka factory. Yes, the Willy Wonka factory uses it, but they don't grow it. So chocolate, so the products of the New World, so Africa and the Caribbean again and South America are producing the chocolate, but it's not just cocoa powder in it. That chocolate is as defined as it is because it is based on chocolate complex of sugar. We set up a whole set of desserts and sweet. We set up a whole alcohol industry. We set up a thing like molasses, which comes as an ingredient in many of our foods. Every Canadian knows about your baked beans, which is usually molasses in it or sugar, whichever one you're getting. This is my bread that I made. It's one of my favorite recipes. It's a Nova Scotia oat bread, but it is brown because it is made with molasses in it, okay? So the cuisines change throughout the world on the basis of the slave trade that is providing us with cheap sugar, okay? I do make my own bread. I take it as it's a time to just relax. Me and my kneading. I'm doing that after school today. I'm making some bread. It's just relax and just knead flour. How complicated could life be? All right. So to preserve with sugar is very tricky. It's not as easy as preserving with salt. I mean, technically you could, but the problem is if I just dump sugar onto food, it'll get like, the crystals will just stick over everything and it doesn't just come off. It tends to, the crystals of sugar tend to coalesce together and get hard and I get a rock candy and that's not what I want. It's not like the salt that's easy to flake off again and work with. And also I can cook it. And when I cook something that was made with sugar, it does change. So we're going to use a few tricks. So candying becomes a technique. So this is a candied cherry. This is the last candy cherry I will ever buy. It is so sad. I cannot believe how terrible it was when I had it. It's awful. It truly is nothing but sugar. There is no cherry in there. I have no idea what they did to this poor cherry, but I was desperate at the time and I tried to buy it and it was awful. And I read the ingredients. I'm like, well, no wonder. I think what they do, and this is a commercially produced cherry, I suspect what they're doing is they're picking green cherries so there is no flavor in them. Then they preserve them, and we'll talk about how they do it in a second, so that they stay nice and firm, because when you look at the ones I've done, they're not going to be firm. But they're going to do them with green so that they're nice and firm, and then they're just going to put all the fake flavors and the synthetic flavors and the coloring and everything in it, because there's really no cherry in there. It's just a cherry in shape. So yesterday I decided to check if I could do this for class. I was like, okay, let's take on this. So I made candy cherries. Where's my candy cherries? They are currently soaking, so whereas those ones are dry, I was concerned not to put them straight into alcohol. I have put them into alcohol. So as you can see, it's Canadian cherry, so it's darker. It was ripe. It is firm, but not as firm as theirs, and it does taste delicious. This one's soaked in an awful lot of brandy, so I will not be having it during the middle of my class. That's probably not the wisest. I'm just going to pop that back in there. Okay, and we'll talk about how I managed to do that. By the way, they're purposely soaking in brandy. That was the point, because as I mentioned, my family is West Indies. What do you think you're going to use this for? What do you think this is for? I'll give you a hint, it's for Christmas time. What would Mrs. Kelly Maharaj, come on, if you know anything about Western culture, what was she after buying such horrible candied cherry? And what would she be trying to get candied fruits for and soaking them in alcohol? Fruit cake, you got it. This is for making the famous rum cake. I have started. This is going to be one awesome rum cake next year. You're going to have real fruit. It's going to be it's going to be the best. All right. So that's not for eating. That is for making the traditional rum cake. Leave that alone. And I can make it now, and I don't have to worry about it till the summertime. I'll try to make the cakes and then wrap them, etc. Okay. But how did I do it? So let's start off with the principles. I need to get me, oh, it's right here, paper towel. Let's just show something about sugars. Let's understand what we're dealing with sugar. Firstly, is sugar soluble in water? Okay, you know. Yes, of course. So if I dissolve this in, it should dissolve, right? Let's do that. I'll put some sugar in there. I put some water. I'm going to use my sturdy spoon. That's fine. If I stir it, it should go clear. If it dissolves, the solution should go clear. And I put a fair bit of sugar, but it's starting to clear up. I can still see some crystals in there. I'm going to add a little bit more water just to speed it up. All right. Okay, so it's almost clear. It's a slightly brown liquid, even though, because I don't buy the white sugar. I like to buy the unrefined version, where it's got a little bit of brownness to it. It's not brown sugar technically. It's just unbleached, essentially. They didn't take off every last bit. That's what the molasses is, when they take out all the brown stuff from the sugars. It's not just pure sugar in there. The plant makes other things, and so those other things is what's making it brown. That's where you get the molasses, the other stuff. Okay, as you can see, it's gone nice and clear though. The slight brownness is because it's a slightly browner sugar than you're probably used to. So yes, it can dissolve. Now, not surprisingly, it dissolves, okay? Now, what about if I made a polymer out of sugar? What would I get? What's the polymer for sugar? So take the glucose and make them into a long string. This is sucrose technically, but let's just go with the subunit glucose. If I made a polymer out of it, what would I get? Couple of possibilities. So glucose, link it up using it. What's the reaction that I would use to link it up? Dehydration synthesis. Excellent. Okay, so it's an anabolic reaction. It's dehydration synthesis. Take those water subunits out between. Okay, link them up. What do we get? What's the polymer going to be? A polysaccharide. Yes. Can you name me one of the polysaccharides that you could get by linking up glucoses? Starch. Voila, cornstarch. Okay, so we're going to work with cornstarch. You can also get cellulose is the other common thing. And if it were animals, you could get glycogen, which is kind of like our equivalent of starch. Okay, so there's a couple of variations, but generally you're down to starch versus cellulose. What's the difference between cellulose and starch? Yes, cellulose is not digestible because it's the beta glucose, which it's okay if you don't remember which one's alpha and which one's beta, but because it's going up and down, you get cross-linking, hydrogen bonding between. So it is much stronger because you're going to hydrogen bond the polymer between itself, and so it's not digestible. I'm going to put this in here. So it's not digestible. Can this dissolve in water? The cellulose dissolve in water. If I put a bunch of cellulose fibers on it, would it dissolve? Would starch dissolve? What are you thinking? Yes, you can get it. Apparently, we're dying for snacks. So I'll have my daughter coming through looking for snack time, apparently. This is so All right, I'm going to put starch. Do you think starch, because this is a paper towel, so one might argue, well, come on, the real problem is I need to break it up a bit. So let's do the starch. This is a powder. I'm going to add water. Is starch going to be soluble? What do you think? Yes? Okay, let's give it a try. Now, I filled the container so you won't think that it's due to it just needed to add more water, right? So I filled it up. Does that look like it's dissolving? Travis, how do I put it back in there? Does that look like it's dissolving? I'll stir it some more. Yeah, that's very opaque, quite opaque. And I didn't put that much in. That's soluble. You can see the light can pass through it, so clearly the particles are dissolved and hydrated the water. This is not. Okay? Now, let's make sure we're clear on why. That is easily dissolved. This does not easily dissolve, but it's made out of glucose. Why not? This is glucose subunits. This is the polymer of glucose. Why wouldn't this dissolve? It may take more time. Sure. Maybe Mrs. Kelly, all you need to do is just let it take longer. True. I gotta tell you, it won't dissolve. It will just settle out. If I left this here, I'll come back and I'll see all the white stuff has fallen out. It'll take a while because that's a lot of liquid and it is a very small particle, but it will settle out and I'll see the stuff on the bottom. See, it'll just sink down. So it's not time. If we had time, I could leave this for a day. Like if this were in classroom, I could say, okay, let's see it in a day or two, but we're just gonna have to accept that it wouldn't have dissolved. So what might be the problem? The interactions should be similar with the water molecules because it's the same, technically the same molecules, same intermolecular forces, so why not dissolve? To dissolve means that you have to go between the water molecules, disrupt the hydrogen bonding, and let water surround you. What do you think is the problem for that polymer? I'll remind you, it's a polymer, a long string molecule. What's the problem? The only difference between this and this is that's a single glucose subunit by itself. Glucose, and I know it's really serious. The bonds are stronger than the one, but it shouldn't, because this is glucose. This is glucose linked together into a long chain. But pretty much we should be talking about the same. If you drew out the diagram, you should see the same functional groups all around that molecule. So shouldn't it have the same intermolecular forces with water? So why not dissolve? Remind you what dissolving is. It means that the particles can fit between the water molecules and that the water can surround it. What do you think is the problem? It's too big, Abdul. Yes. Sorry, I'm saying names again. Yes, too big. So we can't dissolve, okay? We are going to exploit this, though. Leave that aside for now. So sucrose can dissolve. Glucose can dissolve. The sugars, the small ones, will dissolve, and therefore I can create a solution. In this case, I can create a hypertonic solution. So yesterday, I took my cherries. I put it on the stove. I used heat to speed up this because I'd like to do this, you know, in 20 minutes or to an hour, rather than having to do this like, you know, over 2 months. Heat will speed the particles up, move them faster, everything will happen faster. So I put my sugar on the stove, about 50% water, 50% sugar. I also put in some honey, because remember I said part of the problem with sugar is that it crystallizes so well. So a liquid sugar kind of disrupts the crystal structure because it will stop the crystals from touching each other as often, and so crystallization is reduced. So I put a little bit of honey, but it's primarily just sugar and water. And I boiled my cherries in it, which is why they get softer a bit, because I'm boiling them, so they collapsed a bit in the heating process. That's understandable, but they still came out fine. Now, putting them in a strong solution, a high concentration of sugar. What kind of solution did I put them in? So I put them in a solution with a very high concentration of sugar. It's pretty much saturated. I made a syrup with it. In fact, I'll show you the syrup. It's red now because of cherry juice. So I haven't thrown out the syrup because if I can find a way to use it, it is. But as you can see, it's actually fairly thick. This is just my sugar water. That's how sugar water runs. This is how it is. I run it on a plate so you can see that it's actually kind of, okay, it runs not quite like maple syrup, but it is going to run a lot slower than if it were pure water, okay? So it's a high concentration of sugar. I'm not going to taste it. That's just going to be straight. And that's not good to drink. I've kept it in case I can use it to like do something like cranberry, preserved cranberries or something. So what did I do when I put my cherry? So I take cherries, a nice sweet fruit, by the way, and I put it into a pot with a lot of sugar and water. What kind of solution did I put it in? It's a hypertonic solution. Okay, you take it from there for me. What will happen in the hypertonic solution? So it's in a hypertonic solution. What happens? Come on, you can figure this out. The water in the cherry will come out and it will shrink. Okay, Tina, I agree with part of your answer. Tina's so sorry. It's not so silly. I can't resist. I'm so sorry, folks. The water will come out of the cherry and it will shrink. Okay? But I don't agree 100% with Tina. Can somebody tell me what part they agree with and what part they disagree with? Tina's forgotten something. Or she's not taken it into account. Maybe it's not that she hasn't forgotten it. She hasn't taken something into account. It'll come up more like dry. Okay, it's the shrinking part I object to. It's a plant cell. This is not a fish. Not a fish. So what's different between the fish and the plant? The cell wall, right. The plant has a cell wall, so it cannot technically, not technically shrink. The inside can shrink, not the outside. The inside of the cell can shrink away from the cell wall, but the cell wall remains, which is why those still look like cherries. Softer cherries, but they still look like cherries. They do not look like what a poor dehydrated fish looks like. Okay, the shape of the cell is still there, but the inside has collapsed away. You're not going to have a vacuum. This is not space. What do you think happens now? What do you think fills the space? Is the skin still there? Yeah. I'm going to give you a hint. This is paper towel. What do you think it's made out of again? What material is this, really? I'll let you figure that out while I go get a strainer. Barely fits, but it fits. All right, cellulose. This is cellulose. It's paper made from the fibers of plants, the undigestible parts of the plant. This is just cellulose, okay? So nobody knew that, but that's okay. That's cellulose, okay? So it's the cell wall. This is basically composed of cell walls. That's what paper is. Any paper product is cell wall. I'm going to pour some syrup through. Can the syrup that I put the cherries in, can it go through a cell wall? That was the question. Well, it didn't immediately run through. It's taking a while, but it does look like it's starting to drip. I'll bring it closer. It's dripping through. So it's not exactly running through, but it's dripping through, isn't it? So is it permeable? Is the cell wall permeable to the sugar solution? Yes. Not highly permeable, but permeable. It'll go through. So Mrs. Kelly-Marhouse just has to be patient. She's going to speed it up by heating it. If this were hot, it would go through faster. I heated it up. So I put my cherries in the solution, and I know osmosis, and I'm heating everything so it'll be faster. Osmosis will drag the water out of the cell. The inside of the cell will collapse, but the cell wall will remain. And my sugar solution, if I'm patient, so after I turned off my stove, I left my cherries sitting in the pot of syrup for the rest of the day. So I did this in the morning, then I went to class, I left it sitting all day long, and all day long, my sugar solution can slowly go through the cell wall. So when I take a cherry out, what am I really taking out now? What is my cherry filled with? This is a complicated snack. My cherry is filled with cherry. You use hands? Yeah, the spoons are there. They're clean. Those are clean. You can have them. Yes, go ahead. I just took them out so I didn't have to go in the drawer. Yeah, so it is now, this is what candying is. Candying is, it is going to be like the salt process, but we want a candy product. So we're going to do preserving, but we're going to get candy out of it too, because we are so craving sugar. We actually love sugar. We're not just interested in sucking the water out of it, but candying is a process of preserving that actually does give us a sweet product. Very different in some ways than the salting process. Salting was just about dragging the moisture out. And the salt that you get from that food is because it's just coated in the salt, really. But in the case of candying, I want to do a two-step process. I want to pull out the water, and then I want to use, I can only do this with plants, by the way. I want to use the process of understanding that I've created a vacuum inside of the cell, which is going to get filled with something, and I would like that something to be sugar. So water goes in, and it fills my, so the syrup, sorry, goes in and fills my plant cell up in the vacuum it has been created. And now I have a candy product, which is so high in sugar that things can't live in it. it's sweet and lovely, and I can ship it around the world. And now we start having all these candy products. So the slave trade didn't just give us sugar, it gave us a whole new way of preserving, which is known as candying. And so then we end up with candy. Okay, we are at 3 o'clock now. So I'm just going to close it just because I want to add one more thing in, which is the polymer. Okay, starch is not soluble in water, but we have found a little trick for this. So if you notice, it's starting to get clear, but that's because the cornstarch, sorry, it's on the bottom. You can actually see the layer of the cornstarch there. It's just falling out of solution right now. I'm going to stir it back in for a second. So I don't want it sitting on the bottom only. I mean, it would work still if it was on the bottom, but then I'm going to have to clean that. I'm going to pop in the microwave for a second. Okay, so while that is going, I'm just going to explain what we're going to do there. We're going to illustrate that much of what we've done when we talked about water is about taking it out of food. But also, and that's great if my trick that I'm looking for is preservation. But there's one thing I could point out where the polymers become important, which is that when dealing with fresh food and I'm cooking fresh food, I actually don't usually want to suck my water out, okay? That's great to preserve, but not always great for cooking fresh food because I don't like to live on dehydrated food. It doesn't taste that good if that's all I ate. So fresh food is obviously important to me. One of the cultures that has done an excellent job of using the polymer tech, using polymers to their advantage, is actually Asian cuisine. They have come up with some brilliant ideas on how they've got a number of techniques they use with starch that is particularly brilliant. And the everyday stir fry is one of the examples. So if you've ever had an excellent stir fry, you will know that there's something unusual about it in that the food, the meat tastes succulent and moist and not dry. And then when you go home to try to make your own stir fry, many people are disappointed on how dry the meat comes out because firstly you season the meat, which means you put salt on it usually, and the moisture gets dragged out. So you dehydrate your chicken and it's not a plant, you literally shrink the cells and everything. Then you cook it, which only makes the fibers and the protein shrink even more, and then more water is released. And so you get this dry, fibrous chicken in your stir fry, and you know you cooked it and it wasn't done in one of those places that you feel like the restaurant does an excellent job. But it's because the restaurant is doing a little trick that we're about to show you how to do. Oh my goodness. I got enthusiastic boiling. Here, I need a napkin. Okay, so I need to clean my microwave after because I got a little too enthusiastic. It's hot. So this is the cornstarch. It's just come out of the microwave. So remember, all I did was I put cornstarch in water and then I heated it. It is not, you can actually see that there's gobs inside of it. And it's kind of jelly-like now. This is actually called, it's a gelatinizing process, it's called, okay? So the question is, what happened? Why did the starch, it was insoluble, now it appears to be opaque, not transparent like it's dissolved, but not milky like it's undissolved. It's kind of cloudy-ish, like, and if I did it longer, it would get clearer, but not like a solution. So what gives? What's happening? What do you think happened to the starch when I heated it? So it went from insoluble to, I don't know, not quite soluble, but not insoluble, somewhere between. What do you think happened? Yes, it absorbed the water. That is technically it, okay? But we're gonna add a little to that. It absorbed the water. Remember, paper towel can't dissolve. So polymers are not going to dissolve in water because they are too big, but they are still hydrophilic, so they absorb water. When I put starch in here, it was absorbing water just fine. It would have been wet. If I took it out, it would have been wet. I could have done that to show you. be wet, it would have been absorbed, but it can't stay in solution. What do you think has happened when I heated it? That actually, in a way, it upped the absorption. What do you think happened to the polymer? The long chain. It's full of water around it. What do you think happened? It unravels. There's some, it's not a protein, so it doesn't have a complex three-dimensional shape. It does have a bit of a coil to it, but not really. So, but that's a good guess. Because if it were a protein, that would probably be an important thing to think about. But not a protein. This is a polysaccharide. So the answer is, why couldn't the cornstarch originally dissolve in the water? Remind me again. It was too big. Now it looks like it's kind of partially dissolved. What do you think happened when I put it in the microwave? I'll give you a hint. A chemical reaction occurred. Can you guess what chemical reaction? The only things you had in that microwave is water and a polysaccharide. What do you think happened? Hydrolysis, yes, water broke it up. It's still fairly big molecules, but it's broken it up. So instead of very long polymer now, you got a lot of short chain polymers. It's smaller. And so it can fit more between the water molecules, so it's more absorbent. And so this is a highly absorbent. The water is fitting in between it. It's still not a proper solution, but it's closer to a solution with the water all around the cornstarch. It's like one big tissue paper. So that's the trick that is being used in Chinese food. When they season the meat, they season it with salt and pepper and dry garlic usually. So you don't even notice that it's on there. But the salt will drag the water out, except they stop it. They sprinkle the meat after they've seasoned it with cornstarch. Just sprinkle on the dry cornstarch and mix it in. And then as the water is trying to get out, the cornstarch creates a layer on it where it's absorbing the moisture, not letting it go anywhere. And then when it hits the heat on the wok, you literally start to break the chains, and any water that continues to attempt to get out as it's cooking continues to get locked around the chicken, keeping it there and stopping it from getting out. And of course, if you add any sauce in, it drags in some of the sauce and keeps it coating. So that chicken isn't anymore technically just chicken. It's chicken with a highly hydrated layer of cornstarch on top of it. And that's called velveting. They call it velveting the chicken. They velvet the meat in Asian cuisine. And that's how it's done for many cultures, Asian cultures. They're velveting the meat by employing the technique of working with their cornstarch. And they can get some pretty nice, silky, delicious meat out of it. Okay? So I hope this helped to explain some of the things that you might have seen your parents doing in the kitchen, or maybe you see them on cooking channels on YouTube. So hopefully you can try them out. I hope that it helps you that by seeing how this biochemistry is working in the kitchen. It's like a TED Talk with the people walking behind you. I hope this helps you at least understand, because if you can understand how it's employed in everyday life, that helps your thinking process when you're doing questions on your test, etc., where you got to think your way through, because you sometimes compare it to what you know in real life. So that was the point of today. I do hope it gave you an understanding of how our cultures are intertwined. It wasn't the major component of today's lesson, but understanding that human food ties our cultures together. It is tied up with who we are as people and who we are as cultures. It is tied up with the history, both the positives and the negative parts of our history. Food has traveled between us. Our cultures travel with that food. Our techniques travel with that food, and we've learned from each other. The good news, if there's such a thing out of the slavery, if there's any such thing as such, because it was a terrible era, but we did learn how to mass produce our food from it. And eventually we did it without the use of slave labor, which was a terrible thing that we as humans did. But today we do know how to mass produce and refine and use it. And the principles were laid down on the slave trade. It's true. And it was terrible and it was wrong. But I'm glad to say that humans have moved away from requiring such brutal systems to be in place to produce food for ourselves. And that's good. I mean, we still depend upon cheap labor, which is not good. We should do better. But definitely, the ability to produce a large amount of food and then employ it using our scientific techniques that we have to preserve, to keep our food supply going, that even in wintertime, I can have just about anything I want to eat. I can have cherries, I can have meat, I can have just about anything. And I don't necessarily need to have it shipped to me to have had that. I just have to know how to process and use it to have it. Okay? So I hope you found it interesting. I hope it's helpful tomorrow that you think of some of these things when you do your test. Okay? If you have any questions, I'm going to turn off the recording so people are free to talk about anything they want. But if you have questions, you can stay on. And if you don't, you're free to go.